So this is 8.5. And once again, we are talking about not means, but proportions. We're talking about hypotheses, inferences of proportions. In this case, we've got two samples. And again, a quick refresh would be to go back and look at 7.5 and the mathematics that we used to find the mean of two proportions. So again, 7.5 talked about the mean of two proportions. In this case, we're not talking about the mean, we're talking about hypothesis testing. But the mathematics that we use is going to be very similar, very similar. Okay, so when it comes to two proportions, two samples of proportions, we're not going to play around with dependent and independent. We're just going to assume that they're both independent. Okay, so no dependent stuff, they're both independent. So that means you're going to have two samples. So we need the size of each sample. We need the p-value, the proportion of successes of each sample, and consequently the q-value, the probability of failure of each sample. Okay, the null hypothesis is, once again, there's no difference between the p-value of sample 1 compared to sample 2. So this says no difference, that they are the same. Okay, that the sample 1 proportion is the same as the sample 2 proportion. Our alternative hypothesis is going to be, no, they're not the same. One is less than the other, one is greater than the other, one is not equal to the other. And once again, I know you're getting tired of seeing this, but less than means below this area, less than. Greater than means this area here, greater than, and not equals to means both. Okay? So depending on how we set that up, determines which area you're looking for. And then you're going to find that area. That area is going to be called a p-value, and you're going to take that p-value and compare it to a threshold, usually 5%. If the p-value comes in below, that's good for us, reject the null hypothesis. If it comes in above the 5%, bad for us, null hypothesis remains king of the mountain. So once again, to confirm that this is a binomial distribution and we want to make sure that we can use a normal curve to estimate it, we have to make sure that n1 times p1 is greater than 5 and n1 times q1 is greater than 5. We also need to make sure that n2 times p2 is greater than 5 and n2 times q2 is greater than 5. So just make sure that those multiplications are greater than 5, and they're going to be. Okay, so how do we calculate things? It's a little bit different, In this case, what we want to do is we want to find something called P bar. And P bar is kind of like the mean of the probabilities. You take the sum of the successes from both samples. Oh, and this should say a 2. So this should be x2 and this should be n2. Sorry, I'll make that adjustment and upload it at the end of class. So you take the sum of successes and you divide it by the sum of the trials. That gives you something called P bar. And then you just find the complement of that in order to find Q bar, okay? So once you have these, this is the equation that you use to, aren't you glad you don't have to do this by hand, all right? Like, okay, everybody, here's the formula. Punch these numbers into your calculator. So glad that we use Google Sheets and an algorithm in order to calculate this. So this is how you find your z-score. Remember, this guy here is probably going to be 0. And so the formula, and this is probably going to just go away. So the formula becomes p hat of the first sample minus p hat of the second sample divided by, and this is where those bars come from. So this is p bar and this is q bar. Okay? And those numbers that we calculated up here, remember p bar and q bar, you use them in this calculation. In the previous section, we used A and B, like we used an A number and a B number, and we put those into a calculation. In this case, we're using P bar and Q bar. Once you do this, out pops your z-score. And then what are you going to do with that z-score? You're going to plot it somewhere. So the z-score is going to be here, maybe, and then you're going to find the area above that z-score. Okay, so once again, this is going to be done by Google Sheets for you. We've got an algorithm that will calculate this. So everything else here is what I'm saying. This is 0. So this part here basically explains why that is equal to 0. And then once you have that z-score, then you can either use a table, a spreadsheet, or a website to calculate the p-value. You're probably going to use the website, or the spreadsheet, pardon me, the Google Sheet. Once you have that p-value, you compare it to the alpha value that we have, the 5%, and you either reject or you fail to reject. Simple as that. So all that we're really doing is tweaking things a little bit with this p-bar and q-bar. So hypothesis test for two proportions. So you go out and you survey 1,000 randomly selected males, and you find that 231 of those randomly selected males exercise once per week. You then go out and survey 1,200 females, and you find out that 176 of those exercise once per week. Okay, does the data show that the proportion of males who exercise is greater than? So greater means above, right? So again, when you see that greater than, you're thinking, okay, we're going to find some z-score, and we need to find the p-value that is above that z-score. So that should trigger in your brain when you see greater than. We want to test at the 5% level. So we take our data. We need to find the sample size of both male and female, the p-value of both male and female, and the q-value of both male and female. And then we're going to state our null hypothesis. Our alternative hypothesis is that the male is greater than the female, and we're going to test at the 5% level. So do we have a normally distributed situation? Can we do this? And if you go through, you'll find that, yep, this is true, and this is true, and this is true, and this is true. So go ahead and proceed. So here's our data. Here's our p-hats for both male and female. Here's our q-hats for male and female, just the complement of each one. This is our calculation for p-bar and our calculation for q-bar. You take all this and you throw it into the z-blender, and out pops a z-score. And once again, this z-score means that if there's a population with no difference between the two, our sample is out here at 5 standard deviations away from the mean. So 1 standard deviation, 2 standard deviations, 3 standard deviations, 4 standard deviations, 5 standard deviations above the population proportion is where our data is. And we want to find the area above that. My guess is this is a very small area, because 5 standard deviations, right? Like that's huge. This z-score, when you do enough of these, you'll start to develop an intuition for it, like whether or not the area is going to be a big area or a little area, just by looking at the z-score. Like, yeah, 5 standard deviations away from the mean. That's going to be a very small area. So we take that 5.07, we plug it into Google Sheets, and look at the area that we get. Very, very small area. So because that p-value is much lower than our significance value, that's good for us. That means that we get to reject the null hypothesis and replace it with our alternative hypothesis. So we can say, yes, there is enough evidence to show from our sample that the proportion of males who exercise once per week is greater than the proportion of females who exercise once per week at the 5% level. Okay? And so that is the theory behind 8.5. Now let's go in and take a look at actual problems. And so we'll go into the 8.5 problem set. And I'm going to put the 8.5 tech tool over here, and you can see in the 8.5 tech tool, we've got sample 1 here, we've got sample 2 here. We're going to find the number of successes in sample 1 and sample 2 and divide it by the total number of items. So here is the problem set from 8.5. A new beta blocker medication is being tested to treat high blood pressure. Subjects with high blood pressure volunteered to take part in the experiment. 160 subjects were randomly assigned to receive a placebo, and 260 received the actual medication. high blood pressure disappeared in 90 of the controls. So if we let sample 1 be our control, we drop a 90 in there out of 160, and then 159 in the treatment group, and there was 260 in that treatment group. Okay, so sample 1 is our control, sample 2 is our treatment, and here are the p-values for each one of those. So you can see the control came in at about 56%, the treatment came in at 71 or 61%. These are the q-values. The confidence level is 1%, so that stays the same. And here's the calculation for p-bar and q-bar. You're not going to need these numbers, but that's just part of an intermittent step to get the final calculation of the z-score. So you take that p-bar, q-bar, and the other things, and you put them together, and this gives you a z-score. So this would become my new p-value. My test statistic is correct, so that's good. That tells me we did the calculation right. Not too bad. I mean, it took us all of what, like a minute and a half to do this problem. We plugged in the values. The arithmetic was done for us. It's the conceptual part that we've got to make sure that we pay attention to.